Okay, good morning everyone. I want to start by saying thank you to Sato-san and the organizers for having me here. It's a real pleasure to be back in Japan. I was here the first and the previous time in 2006 in Kyoto for a scientific conference, and then now it's really nice to be checking out Kobe. I had the pleasure also of seeing a bit of the city yesterday. And then regarding the comments here first, so I must say I broke the rules yesterday and I did take some photos of the slides because I didn't know it was forbidden, but if anyone here for some reason wants to take slides or photos, I personally don't mind. But okay, I'm going to talk today a bit about setting up a distributed HPC plus quantum computing network, and based on experiences that we had of setting up some sort of a prototype of this up in Finland at CSC in collaboration with VTT, the State Research Institute, who actually has the quantum computer. And for those who don't know CSC, so very briefly, one of our main purposes is to provide supercomputing infrastructure to the Finnish users, academia, and also increasingly now, I don't know if there is any pointer here, apparently not, but increasingly also for industry. And we have pictured here, we have Lumi that we are hosting up in the northern Finland, 600 kilometers north from our main offices. Well, it's a good place to have a supercomputer. It's cold outside. I think the mean temperature is 2 degrees Celsius around a year. So there's this usual joke that you cool down the supercomputer by opening the windows. Of course, that's not really true. But also here in the picture there, to the left, no, to your right, is pictured the quantum computer, the first Finnish quantum computer built together by VTT and IQM. And much of the story is, as I said, based upon our experiences of setting this connection up, and also on our ideas of how to actually implement these things. But I want to start out by saying that this is, of course, a rather complicated task, as any of you in the audience who have been dealing with this, and well, in principle, any new sort of infrastructure that you want to set up. So this is the main people at CSC who have been involved in this work, but I also want to stress that this has from the beginning been really a collaborative effort with also other institutes in Finland and especially also abroad. But if we start a bit by having a bit of a motivation, I guess for many of you this will not be any news, but I just want to bring it up here. Anyway, so why are we, and by we I now mean an HPC center, interested in quantum computing? Well, I want to first stress again something maybe obvious, but quantum computers will not replace supercomputers, so instead the two will merge. And this means that it is really important to, from the beginning, stimulate this co-creation and co-development between the HPC and the quantum computing communities, which are, we have to admit, talking a bit different languages, at least from the beginning. And it's important to really start this work of talking to each other immediately. And that is, of course, going on in many places around the world already. But the motivation for this is that our end users will need early access, that means now, to this HPC+QC infrastructure in order to make whatever workflows they have quantum ready. And much of this is, of course, also still basic research and also software development and so, but that, of course, has to start now, even if we know that quantum computers, I'll come back to this a bit later, but quantum computers right now do not provide any speed-up advantage to a general user who just wants to see whatever code he or she is running right now go faster. But this transition is really difficult, not only from our point of view, but especially from the, I would say, from the user's point of view, because as many of us here who have been working with HPC for a while has seen the transition from classical CPUs to GPUs, And that's a transition that is still going on, especially for more complex scientific codes. And that has taken more than a decade to even get going, this transforming the code base from a CPU-based code so that it can run efficiently on GPUs. But now when we go to quantum processing units, it will be a much more difficult journey because you just don't recompile your program so that you run the same program on a new hardware, but you have to rethink the whole problem from the beginning. And this will require lots of time, resources, and support. And especially this support part is, as I see it, one of the main tasks of HPC centers. And I also think that HPC centers are really a natural starting point for this collaboration and putting all of this together, because we already have all the necessary basic services in place that have taken, of course, decades to really fine-tune, and of course the work is still going on there. But there is user authentication and administration of users, resource allocations we have all put in place. There's storage, high-speed networks, and, well, of course, then the classical supercomputing resources. So all of this, the basic prerequisites for actually setting up an infrastructure for several users is already there. And also we actually have the end users, so those who are running codes that really require supercomputing resources, so they are already our users. So we have a very good touching base with who could potentially be interested in this quantum accelerated future of HPC. So I said we need to prepare the end users for this hybrid form of computing. And here, HPC Center, so we can help, but we cannot do this work alone because it requires plenty of development, and also it requires plenty of basic research. And some supercomputing center, HPC centers, are involved also in basic research, like Riken here, but for example at CSC, so we are more an enabler of research than actually performing that much really basic research to publish in scientific journals ourselves. And to really get this going, no matter if you do it in-house in the HPC center or not, you really have to engage the end users, because we are still building this up for them. And that's why we need to listen to them from the beginning, just so that we don't set up something that end users will not find very interesting in the end. And these end users should be both from academia and industry, because I think it is important to really get aboard as many as possible from the beginning. And for this we need some sort of quantum carrots. We'll come back to that as well, but there has to be some incentive for the users to jump aboard and together build up what we are building up. But okay, we first need to set up the computational infrastructure. And today I'm going to talk about a distributed HPC+QC infrastructure, and I want to emphasize from the beginning that this is of course not the only way to implement this. This is the way that we are doing it, and we think it's a good way, but for other purposes there's some other approaches to this, but we'll concentrate on this approach today, and we'll see what it means actually. You can divide the method of connecting HPC and QC in three main categories. So you can have these standalone systems where you just have your HPC centers, the blue server boxes there, and then you have a sort of cloud connection to a quantum computer somewhere. And then you have the co-located approach where you actually place the quantum computer very close to the supercomputer. So on the same premise, on-premise quantum computing. And then we have the third category here, the distributed one, where actually the quantum computer and the HPC resources, they are physically distant. So they don't need to be in the same house, they don't need to be in the same city, they don't need to be in the same country. And all of these levels here so come with different levels of complexity for setting up the full software stack for this, and I would say in increasing order of complexity as well. As this is a question that often pops up, I want to spend a bit of time on this discussion of latency between the quantum computer and the supercomputer, just to see how much that affects practical quantum calculations. And this is from a paper by Travis Humble and co-workers, which I hope you can see it there, shows a bit of this time scale of different processes when you are doing quantum computing. And we can see here that the blue box there, which is the very short time scale from nanoseconds to microseconds, that involves error correction, so real-time error correction of your quantum computer. And we will not really touch upon that today. Instead, we'll look at the applications, the green boxes and the red box there, and the main point here is that the time scales from this starts from seconds. And that will have implications for the problem or the non-existence of the problem of latency. So just for those who might not be that familiar with quantum computing from the beginning, so one of the major classes right now of actually doing quantum computing is to use these hybrid algorithms where hybrid refers to that you do some parts on the classical machine and some parts on the quantum computer, and in this case especially referring to these tight loops of where you do purple box of classical computations and prepare a quantum state that you then compute on a quantum computer in the blue box there to the right. And the idea here is that there is this optimization procedure going on where you constantly, in a feedback loop, do a quantum calculation and then a classical calculation. And now if you think of this, so the blue box and the purple box need to communicate with each other, and when the quantum block and the classical block are fast, so that it takes very little time to run them, the communication has to be even faster, because otherwise communication becomes a bottleneck. And with present quantum computers, QPUs, we know that decoherence actually forces the quantum block to be fast, because the calculation has to be fast, because otherwise you only get garbage out. And also because of that, it means that the actual calculations are not very complex, so also the classical part there will take no time to run. So when we have these quick loops, this standalone approach, the first one there, the cloud approach, creates too much overhead. So that's dead. We cannot do this if we really want to do variational algorithms efficiently. So we need to have some sort of a classical processing unit physically close to the quantum computer just to keep it feeding, keep feeding the QPU with new input, something to calculate. But now the important point here is that this task, it's a classical computing task, but it's not an HPC task. You don't need a supercomputer for this in any way. So a powerful server is more than enough. And that's what the last row there on the distributed approach tries to illustrate. So we need this orange box, classical powerful server sitting next to the quantum computer. But we don't need the actual supercomputer sitting there. And to motivate this a bit further, if you look at the execution times of algorithms, so these are now some typical gate operation times for superconducting in red and trapped ion quantum computers in blue there. And if you just concentrate now on the superconducting ones that for the moment are maybe the fastest, photonics might bring this down significantly, and that's one of the maybe very good features of photonic quantum computers, but for the moment it's the superconducting ones and maybe neutral atoms and ion traps that are the most mature ones. That can change very quickly, of course, in this business. But if you think of the execution time of 100 gates, and then we usually need to do that about 1,000 times so that we get reliable statistics for this. So already just executing these gates takes 10 milliseconds. And now if you think of the signal in light fiber, so that travels at, well, not completely the speed of light, but very close to it, so 200 kilometers per second. So in 10 milliseconds, it travels 2,000 kilometers. So that means that the classical server doesn't really need to be very close to keep up at these time scales. Okay, we should still also point out that this was just summing up the gate execution time, so we don't consider even qubit reset and readouts here, which will add a bit to that. But let's hope that those procedures will become increasingly faster also with time, which I'm sure they will. But that is the ones that we do now. So that was an example of a 100-gate circuit. But when quantum computers mature so that they actually start doing something useful, we will also need to execute more gates in a row before the algorithm is done. So that means that the runtime of this quantum block, also in variational algorithms, will increase. So it has been estimated, for example, for the QAOA algorithms that to get any sort of quantum advantage, at least counted by the speed up, we are going to need circuit depths that are much deeper than what we can do now. So this shows that we are going to need on the order of 1 million gates in order to get some sort of quantum advantage. Of course, there's algorithmic developments all the time, and most likely this number of gates will go down, but it's still at this order. So when actually we get quantum algorithms to be useful, latency becomes even less important. So here's just the same calculation, but now assuming that we do 1 million gates, and that will already take 100 milliseconds just for one shot. So again, the same thing. When we do actual interesting quantum calculations from the point of view of getting scientific results, the calculation itself takes so long on the quantum computer that it doesn't matter how long it takes to communicate the results back to the classical computer. So this means that actually, in this case, in the future, for many cases, cloud quantum computing will be completely fine. And here's just from another article an example, so that it's not just my imaginary numbers here, but this is an example from derivative pricing with a variational algorithm where in this specific example, so they estimate that one needs about 8,000 qubits and a depth of 54 million gates, and that the calculation will take on the order of seconds. So again, latency doesn't matter. Okay, so let's have a bit closer look at this, the difference between the co-located, where you have the quantum computer sitting next to the supercomputer, and the distributed approach here. So the distributed approach will need a bit more work on the software stack, and that's because of a few main reasons. And one is that we need to have this one additional communication step somehow implemented. So we are not only talking now between the orange box, the classical unit, and the quantum computer, but also the orange box needs to talk back to the HPC cluster, because there will be things that you actually need HPC resources for as well. And we need to set up a system that includes one additional communication step. And also, if you have the quantum computer somewhere else than in the supercomputer center, you're going to have to somehow take care of the authentication so that the quantum computer knows that it's an authenticated user that does the calculation. But the reason why, here are some motivations of why we want to make this work anyway, even if it is more complex, and that is that when this software stack is put in place, it's actually rather easy to add additional quantum computing resources, at least if you do it in a sufficiently general way. Because when you have the software, all you need to connect yet another quantum computer to your supercomputer is to place this classical server next to the QPU. And, well, of course, an internet connection. And this really increases diversity of the quantum computing offerings that you can give to your users, and inclusiveness in the way that you really get also to work together on solving the same problem. And I think this is maybe one of the main points as well, that when you are working to set up something where you don't own the quantum computer yourself, it forces you to collaborate, and that actually gives you very valuable insights from the other side. So you cannot do this alone. If it's not your quantum computer, then you have to work together with someone else. And then users can also access these several QPUs from the same environment, from their same HPC environment that they are used to. And then, of course, from this, it also becomes easier to share the quantum computers, share computing time on them. So for your users, you don't need to buy all the 10 different types of qubit technologies that are out there now, but the users would actually want and need to test on all of these. But when you are sharing the resources, then you can have 10% of quantum computer time, and that is usually sufficient, at least at this stage, for the end users to really try it out, that how does my algorithm work on a neutral atom system or a superconducting one or whatever. And it also means that the quantum computer and the HPC can physically be located in an optimal place. So we can have the HPC systems in large data centers that have sufficient and affordable electric power because they are power hungry, as we heard yesterday. While quantum computers, they don't really need much energy at all, but they do need a shielded environment. So they are very, very sensitive to temperature and vibrations and all sorts of other noise sources. And one example of this is cosmic radiation that already now is starting to affect quantum computers and the qubits there, and which would mean that, well, you need a very, very shielded environment digging down quantum computers underground or so, but you would probably not want to dig down your supercomputer in the ground just so that it would be in the same place as the quantum computer. Okay, a quick slide here on what we have done with the LUMI supercomputer. So in March 2022, we did the first connection between LUMI and the quantum computer. It was actually the Wallenberg Center Chalmers Cal 9000 computer in Sweden, and ran this cross-border quantum job on this. And just after that, we also connected then the Finnish Helmi quantum computer, and we have connected also others that are not online right now there. But the next step is then to really do this on a broader scale, so, which means implementing the LumiQ concept, where we want to, in the first stage, set up this pan-European distributed HPC+QC environment. But of course, as said, so when we have the software stack in place, it's not in any way restricted by national borders. And here's just a picture of the LumiQ consortium, where the actual quantum computer is going to go to the Czech Republic and sitting next to the Karolina supercomputer in Ostrava. But the idea is then to really make this cross-coupling between plenty of HPC centers and also other quantum computers, because that comes a bit for free, so which we can see from this figure. So this is a schematic of how we want to set this up. So the idea is, again, that the user is authenticated at the HPC system, and then we just offload, well, just is the wrong word, but then we offload the quantum part to a quantum computer. So we first set up a connection or software stack for the two highlighted systems there, so the Karolina supercomputer and then this LumiQ quantum computer. But when we have that in place, then we can just add more supercomputers and quantum computers into the mix. And we get these for free, and for free here means with very little additional work. And that's one of the main motivations here. Okay, so to set this up, there are some considerations that I want to mention here, just to give an idea of the complexities involved. But just to reiterate, the goal of the whole exercise is to really set up this general protocol for connecting HPC and quantum computing. That means that we want to have several generic HPC sites and several different quantum computers cross-coupled a bit in the way that is shown there on the slide, or on the image to the, again, you're right. And this protocol, we want to set it up from the beginning so that it's as transferable as possible. Of course, nothing is completely transferable, so we will need adjustments based on the exact systems there, but the idea is to try to take as much of all of the differences into account from the beginning to make this transfer of the software stack as straightforward as possible. Okay, here's some higher level considerations, as I now somehow entitled this slide, but we need to consider that this is really a new experience for the end users. So, and now end users come from two different camps. So we have the users that are already running some quantum calculations on their local quantum computers in universities, university labs or so, but they really have often very little experience with how one does it in the HPC way. And this was really demonstrated well. We had a kickoff of a Nordic project where we put this together, Nordic Quest and in Chalmers, and there Miroslav Dobzicek really pointed out to the audience, who was to a large part consisted of physicists working on the quantum computer, and he explained what a queuing system is, because of course they have never had any need to do that. They just enter directly the calculations into the quantum computer. But if you want to do this in the proper multi-user way, then of course we need to have a queuing system. But these concepts are not familiar to them, and there's many concepts to the other side that are not then familiar to people who are used to using HPC systems and reliable classical computers. A quantum computer is really a device for experiments. It is well, it's supposed to give different answers every time you run the same algorithm, and that's of course one example of a completely new thinking that we need to put into the heads of our normal users. And for the moment, there is a rather low maturity of the quantum hardware and also the software. So there's not different vendors have rather different low-level software stacks, and this is something that we need to consider. And then also this high-level goal of sharing the resources. So that's of course easy to say that let's share, but in practice, when you start doing it, there will pop up lots of these bureaucratic issues. For example, agreeing on who pays for what, agreeing on how to set up the user access, and also if you want to have a production quality system, then you need to agree on who takes care of user support and what parts of the user support and all of this. So actually this is a rather big part of getting it really to a usable experience for the user. So there's lots of this paperwork, let's say like this, in the background, and then figuring out how to do this. But I would say it's still worth the exercise very, very much. Well, on the authentication side, I want to mention a few things here. So one constraint here is, of course, that only authenticated users should be able to access the quantum computer. And here, the way we are setting it up, and that feels natural to us, is that the primary authentication should take place at the HPC centers, because we have all the components in place for doing this, like, for example, resource allocation. But then there's also, when one actually starts setting this up, one notices quickly that it's not only a matter of giving some users access to the quantum computer, one quickly comes also to the realization that, okay, we need different levels of access. And that's something that you maybe don't really have on a supercomputer, except in the way that, okay, this user can use CPUs and that user can use GPUs. But now different levels of the QPU comes in, because the simplest one is to have only these gate-based circuits that you can send to the quantum computer. But actually a large part of the users right now want to have pulse control of the quantum computer, because they are doing some physics experiments or otherwise testing out new error mitigation schemes or pulse optimization. So you need to give more access than just, in a way, a vetted circuit. And this already, when you discuss with quantum computing vendors, so they might sometimes be a bit hesitant to give full pulse control, because if they have sold you a system, they want to make sure that they are not then liable if some user creates some really weird pulses that actually could break or at least severely disrupt the operations of the quantum computer. So you need to have at least this level into account, and then somehow give access to those that you, by some sort of procedure, trust that they will not break the quantum computer. And then there's even a more fundamental level that can be very useful, especially when you want to test out completely new things, is to really let the user modify the calibration settings, the frequencies of the qubits and so forth. And that you probably don't want to give to everyone. But then again, for example, if you want to have the owners of the quantum computers to also access the system through your HPC, then this system has to be in place. Because you have to have some sort of method of letting the quantum computer know that now this is a root level user that wants access. And they need to be enabled, all of these. And then we come to the question of who trusts who. So is it the quantum computer that should trust the HPC systems, or the other way around? And in practice, this might now be an HPC-centric view, but in practice, this is best done by trusting the HPC center to make the connection to the quantum computer, and not the other way around. In many if not most production level supercomputers, you really cannot connect freely to them from the outside. It has to go through specific protocols, so you cannot just open a port on the supercomputer and have that discussing with the quantum computer, while you can do it the other way around rather easily. And then there's also a question do we actually want to transfer this identifiable user information from the HPC center to the quantum computer? And in many cases, you don't. And this is the way that we are putting it up. So users should be able to submit jobs to the quantum computer without the HPC system sending any sort of identifiable user information to the quantum computer. And this is also, to a large part, legislation where you, for example, by GDPR, you are not supposed to send information that you don't really need to send. And also, if the quantum computer gets access to user information, then they also have to have a system in place for protecting the user information and so forth. And in many cases, they don't want to take that responsibility. So then we have to set up some sort of a system of making sure that the quantum computer can trust the HPC center when it connects without knowing exactly who is running there. So we need some sort of a metadata scheme for this, and that would associate some sort of an identifier that, for example, would include a user ID, it can be pseudo-anonymized or somehow the job ID and also the name of the HPC site or some sort of a identifier for where is the connection coming from. Because if you remember, the idea was that we are not only setting up now connection between one HPC center and one quantum computer, but the quantum computer is expected to get connections from all sorts of places around the world. And then it will be interesting also from just user access policies to know where it comes from, because the quantum computer might also want to prefer connections coming from a specific place, and this is just the fact that you have to take into account that not all users will be treated equally, and that's of course in the full right of whoever actually handles the quantum computer. Then we also need to send some sort of calibration information in both directions, depending on how you want to do it. Usually it would come from the quantum computer to the supercomputer, but as mentioned before, you might want to change those as well. And then you need these figures of merit, so decoherence times and fidelities and so forth. And it's not only interesting for the user, but increasingly publications also require that if you actually publish a quantum computing experiment, then you need to provide these numbers. And that's some information that for each job has to be sent back and forth between a quantum computer and a supercomputer. And then, of course, it will be interesting to also have some sort of a real-time health check for the quantum computer available, and so forth. So then we can think a bit of the data transfer that we actually need between the HPC and QC system. And one thing that we, of course, need to send is information on what to compute, and then the other way around, the results back there. And in increasing order of how much data that requires, so we have these quantum-only circuits where you just send whatever gate sequence to the quantum computer, and that doesn't take much space. And then you can have a predefined variational algorithm where you send a bit more information, where you want the orange box there to have maybe a library of some variational algorithms that you can then run there. But then you can also rather quickly run into a situation where you want to have a fully user-defined container to run on the orange box, where the user really defines exactly what the classical part of the algorithm, for example, wants to do. And that easily becomes then gigabytes of data per job. And of course, there's a big difference also in transfer time if you're going to send a kilobyte or a gigabyte over the network. And this is something that you need to consider. And here, again, you need a rather high-speed network to make this efficient, unless you do it in the background and interleave the jobs, which is probably the way to do it. And well, then you also want to have some real-time status monitoring going on automatic, because, well, the job can either be canceled or crash on the HPC or the quantum computer. And then you don't want to leave either of them hanging and just waiting for something to happen. And then there's a question of the resource tracking. So on the quantum computer side, you need to have, well, you don't need to, but usually it would be very nice to have some sort of a counter that counts either how many shots you have been executing or how much time you used on it, because in many schemes, well, just like in normal HPC resource allocation, you need to track how much resources were actually used. And then there's this challenge that I would call the user expectations. And some unnamed users might have questions like this, that, okay, now you got a fancy new quantum computer that cost 10 million euros or 2 billion yens. So why didn't you buy NVIDIAs instead? Those I could use immediately, and you would get a big bunch of H100s for that price tag. So in other words, where is the quantum advantage in having a quantum computer? And this is something that a public HPC center, at least, really needs to seriously consider. We should not just buy them because they are cool toys. We need to somehow motivate this very well to our funders and also to the users that we really are doing all this for. So of course, in some cases, you can motivate this by research. So you need to have some research equipment to really do something. But I would say that the important point here is that we really are preparing for the future, and we need to look further ahead and really believe that quantum computing, or believing that quantum computing will be usable for the general end user at some point in the future. So we actually just need to do that work now, and then we need to have real quantum computers to do anything. And well, then as mentioned, so we have a completely new user base. So we have these users that are unfamiliar with HPC, and they are a class of users that we, as HPC centers, have not interacted with that much before, and that also does put a bit of learning on our shoulders here. Okay, then a few slides on this, when we could expect quantum advantage, but that of course depends on how we define quantum advantage. And the first and classical, I would say, definition is this wall-time quantum advantage, where a quantum computer helps to solve some problem faster than what you would get if you would use classical binary supercomputers only. And this, I think, is still some time away. It will need still massive algorithm development and massive hardware development before this becomes a reality. And then there's the second one, the green quantum advantage, that was already mentioned here as well, which means that you would use a quantum computer to just get a higher solved problems per kilowatt ratio. And this is an advantage that doesn't require the quantum computer to be faster than a classical computer. It just means that if you can solve a given problem using less energy, then that is in many cases already a real advantage. And then there's this quantum quality advantage, where the quantum computer would provide, by some definition, a better or more accurate prediction or result of your computation. And this would come mainly from the fact that you have to solve problems in a different way when you are using a quantum computer. And I think here we had yesterday a very nice talk about quantum machine learning, where you actually need to just do things in a different way that might come with advantages for the actual results, even if the calculation isn't sped up. It might even be slowed down, but in general, machine learning is a multi-dimensional optimization problem, and then you might, by just doing it using quantum computing, end up in a better minimum of your large language model or whatever. And then we have this quantum control advantage, and this comes from the fact that quantum computers really provide high control of a quantum system. That is what they have to do in order to function. So one really needs to tame the quantum states and really have super high precision of manipulating the quantum world. So, and this actually enables the study of completely new fundamental physics at a new level of accuracy, and also just enables it in general. And the last one I have here is just other quantum advantage. So here I mentioned the carrots before, and well, an academic carrot would be just that you get scientific publications by running something on a quantum computer or developing for a quantum computer, and you get project funding. And that is, sounds maybe trivial, but of course, in the scientific world, it is a rather important thing. And for industry, well, there would be the competence development, and especially early IP creation if you are doing some software here. So you can write the software before you have the quantum computers and have patents on that. And of course, one should not also underestimate the value of PR. So a company that is involved in quantum computing can at least be seen as really a high-tech, on the edge forerunner in technology. Okay, I put some estimates here of when these different levels of quantum advantage comes, and I cheated by just putting some free definable units of time there. The main point of this slide is that number 4 and number 5 are advantages that we actually have already now, and that's something that we need to emphasize to our users. So we have the quantum control advantage, I'll return to that in a moment, and then we have this other quantum advantage that was on the last slide, previous slide. And this, the fourth part here is to actually use quantum computers for something else than computing, mathematics, or algorithms. So quantum computers really can be used as equipments for experiments, just because that's more of a byproduct of what one had to do to actually get quantum computers working. So you really get to manipulate the quantum world with unforeseen and, well, unprecedented accuracy. And here's just some examples of what has been done on quantum computers. So we heard about time crystals already yesterday, but they have also been implemented or made on a quantum computer. And then there was also this paper that, okay, there was some discussion later if it actually was a wormhole or not. But it was discussed that one could create an information wormhole physically on the quantum computer. And also black holes have been claimed to be well, set up on a quantum computer. And this, of course, really is not really computing algorithms, but it's simulating some sort of a real system, but at the same time actually creating that real system. So this also really blurs the line between what is a computational simulation and what is actually setting up a real physical phenomenon. So, and that's something that you really can do now. And there was also, recently there was this article related to chemistry, where one set up a sort of a chemical reaction on a quantum computer, but then with full control of that, could slow down this chemical reaction by a factor of 100 billion to just really see what actually happens during that experiment. And these types of calculations or experiments is something that one really does now. So this is not papers where one publishes that, okay, when we have that real big quantum computer, then we could do these things. These are things that people are doing right now, and it's something that I think would be important also for HPC centers to really focus on at this stage, because this is something that we can motivate already now, that with this 10 million euro machine, you actually get to do some science that was impossible to do before. And here, of course, we need to create some added value of HPC. And there I think it's not enough to just have this resource allocation and so forth. But one aspect here, it was touched upon a bit yesterday as well, is error mitigation, where you actually could do, and well, also pulse optimization or whatever. But if you think of post-processing error mitigation for increasing number of qubits, that already becomes an HPC problem. And instead of just purifying now the results of your variational algorithm or whatever, you can purify the signal-to-noise ratio of your actual physical experiment. And this is something that combining these two powers, the existing power of supercomputer and the existing capabilities of quantum computers, where I think that we should probably make a bit more effort, because this is something that has immediate effect. Okay, then I just want to mention still from an implementation point of view, what probably will be the biggest challenge in setting up this middleware here, and that would be the scheduler. So getting the high-level HPC scheduler and then the meta scheduler that is located next to the quantum computer and takes care of all the inputs that comes in there. Scheduling for HPC and quantum computer is completely different. So on HPC, you have long run times usually. Even just a MPI hello world over 10 nodes, even if it doesn't do any computation at all, on any modern HPC system takes a second or two to calculate, just by setting up everything. This means that the scheduler can take its time when dispatching jobs, so it doesn't matter if Slurm updates its database every 5 minutes or 10 minutes, that doesn't matter. But on a quantum computer, the jobs are, at least for now, very short, so the scheduler really needs to be a super fast scheduler that keeps feeding the quantum computer, so you cannot have the quantum computer waiting for the next 5-minute Slurm update until it runs its next circuit there. And well, another thing that we need to consider here is that on the HPC we have abundant resources, while quantum computers are really still a scarce resource. You have a couple of them available maybe, while you have thousands of nodes on the HPC. And all of this together means that we really need to have separate top-level HPC schedulers and some sort of a quantum computing bound meta scheduler. And I'm running out of time, but I just want to go through these different user groups that affects also the scheduling in a new way. So we can have these short, fully quantum jobs where you just run one circuit, and that's actually rather easy to schedule. And then you have the variational HPC+QC loops, and that's also quite easy. But then you have what will become more important in the future, these hybrid HPC+QC jobs where you really have an unbalanced workload. So you have a real-world workflow where you once in a while call the quantum computer. So you can run an HPC calculation for an hour, and then you want to use a bit of quantum computing resources. And this becomes very difficult for the scheduler. So what happens to the HPC job if there's now a 2-day queue on a quantum computer, or the other way around? So, and then there's the physics experiments that actually can take days to run. Of course, that puts stress on the other users, but from a scheduling point of view, that's rather easy. If you need to reserve the quantum computer for a day or two, then technically that's not a problem. And here I just want to show quickly how we have set it up now between CSC and VTT as a base test system, and we have been running this now a bit over a year and collected information from our users of what they actually want and need, and learning on the go. And I want to stress that this has really been a nice collaboration between CSC and VTT, who has the actual quantum computer in this stage. Here I want to end with just a summary, and I think the main point here is that by pooling and sharing resources, we really can do much more than trying to do everything on ourselves. Arigato gozaimasu.
Thank you very much.